far as I think. I'm about 90% sure of that. Okay, any others from the homework? So again, algebra, be real careful. So I would say the magical step is going from here to there. And then you're like, whoa, super cool. Okay, any others from the homework? Any others? Hands. Wiley, thank you for using your hand. Yep. So first of all, pieces of that look familiar, right? So Ian, can you tell me what e to the t is?
1.
Yep.
Plus x.
Careful. T plus.
T squared over 2 factorial.
Yep. Plus.
Plus t to the third over.
Yeah. Yay. Nice. We're good. What is cosine of t equal to, Chip? What's cosine of t equal to?
It's 1.
Is it 1? Who thinks it's 1? Starts with what? Starts with 1 minus what?
T squared over 2 factorial.
Yep. Plus
4.
t to the 4th. Yeah. Like that, right? We're good with that? If two things are equal, can you multiply both sides of two different things? Yeah, you can multiply sides. You can multiply both sides. So you actually know that e to the t cosine t is equal to 1 plus t squared over 2 factorial plus t cubed over 3 factorial dot 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 times what? 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial. Okay, so here's the thing. You could stop there. That is a proper answer. On the AP exam, they might actually do one more algebraic step. They might do one more algebraic step and ask, what are the first 4 terms? You can't leave it like that. You're going to actually have to FOIL this out. There are an infinite number of terms in each of the parentheses, so you can't multiply all of them out. So what do? There's the first few, right? So let's take, how about 1 and we multiply times the first 3. Is that okay? If we do that, what do we end up with? 1 minus t squared over 2 factorial. I'll move this over a little bit. I'll put it right here. Minus t squared. And then what? Plus t to the 4th over. With me so far? So then we're going to do this one. Multiply times t. What do you get? T minus what? Over what? 2 factorial, right? Plus what? Plus t to the 5th over 4 factorial. Now, could you do that for the next one and the next one? Then it's really just being really careful about combining like terms. Combining like terms. You also have to be careful of the following. I'll move this over. Actually, I'll make it smaller so we can do a few more. Yay, smaller. Exciting. If we do the next one, what's the next term going to be? Plus what? Let's do the blue one here. So times 1. T squared over 2 factorial. Then what? T to the 4th over, this was 2 factorial right there, right? Over what? 2 factorial, not 4 factorial. Don't do that. Careful. And what's that last term you would get if we did times this one? 2 factorial, 4 factorial, right? So if we want to start canceling terms here, what's the lead? If we add all these things together, what do we have so far? 1, right? Well, look at this. A plus t, yes, absolutely, plus t. These two cancel, right? So those are gone, right? So what's the next one here? We have t cubed over 2 factorial and, well, you get another t cubed eventually, actually, because what do you get here? Let's do the last one here. This one, you get what? Yeah, so you end up with minus t cubed over 2 factorial plus t cubed over 3 factorial. What's that equal to? Anybody know? Negative, yeah, t cubed over 6th. If you do it out, that's what it comes out to be. So the first terms are actually this right there. Now, what's the most hard? What's, to me, 1/3. Thank you. It's 2/6. 2/6, 1/3. Thank you. To me, the hardest thing about this is not the calculus. It's the what? It's the algebra. You have to be really careful. Do you see what I did there with colors? And you see how I skipped spaces there to line them up in columns? You see that? You can do that. You will have to multiply infinite series and clean up the first few terms. A common question could be, what's the coefficient of t to the 4th? And you'd have to do it one more time.
So it's not wrong to do it.
To stop there? No, it is not wrong. It is not, to answer your question, it is not wrong to stop there, but on the AP exam, they're going to give you multiple choices that aren't going to match that.
Okay.
They're going to simplify it and then give you 5 things that look simplified.
So is it okay if we did it
So that's 1 plus sine of theta to the negative 1. It looks like a p series, right? Everybody, it looks like the binomial expansion, correct? So what is 1 plus y to 1/2, not negative 1, thank you, 1/2. 1 plus y to the 1/2. So we're going to let y equal to be sine of theta. What is 1 plus y to the 1/2? You need to remember the binomial expansion, right? In this case, p is equal to what? 1/2, right? So this is going to be 1 plus what? 1/2 what? 1/2 y plus what? 1/2 times negative 1/2 over times y squared plus 1/2 times negative 1/2 times what? Negative 3/2 over y cubed. Let's stop there for a second. Can you clean those up for me? 1 plus 1/2 y, and what's this going to be? Minus what? 1/8 y cubed. And I think this is 1/48. It's 1 over 48, I think.
Yeah, 16.
16? It's 2 times 2 times 2 times 6. It's 3 over 40. Oh, it's 1 over 16. Oh, it's 3 over 48, so it's 1/16, like this. Are we okay with this? Okay. Oh, and it's squared. Thank you. Are we okay with this? We good? Is that wrong?
Do they have to use y?
No, but this makes so that you could use a different letter, but this explains it nicely. This is 100% correct. You could write this down on the AP exam, and people would be able to follow it. We're not done yet, though. We're not done yet. Why are we not done? What have we not done? We have to plug in what? But we're looking for not sine to be in there. What does sine theta equal? Can someone tell me what sine of theta equals? Theta minus cubed over 3 factorial plus what? Theta to the 5th over, remember this, everybody? We good? So where do we plug this in? Where does this go? Y. So the full thing is this. The square root of 1 plus sine of theta, we don't want sine to be in there, is going to be 1 plus 1/2 times that thing. So what is that thing? It is legit. Cubed over 3 factorial plus this over what? Minus what? 1/8 times this, right? To the what power? I'm not done yet. To the what power? It's to the 3rd over what? What are we just doing? I'm plugging, no, it's to the square. I'm plugging into the wrong one. Sorry, right there. Because we're plugging it into which one? The purple, right here. We're plugging it in there. You see that, everybody? So here's the thing. Is this similar to what we just did before? Is the algebra going to be not the best right now? Yes. You could go one more term, collect the first 3, and be done. The algebra sometimes will be nasty. There's no way around it. Do you understand what I just did on the board right there, though? It goes on. Do you understand that phrase right here? What am I going to do after that? First of all, answer the first question. Do you understand what I have right there? Are you okay with how I got to the last line? The reason that is powerful is, do you see sine on the left? Yes. Do you see sine on the right? No. That's the whole point, everybody. That's the whole ball game. The whole ball game here is that we've managed to approximate sine, did some nasty things to it. Is sine in the other side? No. At this point, you would just need to do the algebra out. So if you want to do some of it, I'm not going to do all of it. What would you end up with? 1 plus 1/2 theta, right? Minus what? Theta cubed over 12, right? Plus what? Theta to the 5th over what? What is it? Yeah, what's 5 factorial? What is 5? What's 5 factorial? 5 factorial is 120. 120. So what's it going to be? 240. Are you with me so far? And then minus what? 1/8 times theta, right? Plus what? What theta cubed over what? 48? Is that right? Yeah. And then it's going to be minus yeah, we have to be really careful here. I kept the minus on the outside, so just the theta. So this is minus, and this is plus. Plus what? 960. It's 120 times 8. Yeah, 960. So what could you do? You could collect the first terms, right? So what's it going to be? 1 plus how many thetas? How many thetas?
1.
Nope. There's a 1/2 theta there, and there's a negative 1/8 theta right there. So how many thetas? What is it? Oh, shoot! Man, I got ahead of myself. So this whole thing, we multiplied in that 1/8. Are we allowed to do that? No, because what's happening to it? It's being squared. So you have to square it first. Let's square the first few of these suckers. What's that going to be? There's theta squared, right? You agree that there's a theta squared in there because it's theta times theta? And then there's going to be theta times theta cubed over 3 factorial, but there's 2 of them, right? So what is it going to be? Minus 2 times theta to the what? 4th over 3 factorial? Do you agree with that? When you multiply this times itself, you have theta times itself, right? And then you have this times this, right? But then what else do you have? The other way around, like the other multi. You have to be really careful. So I am not going to finish this. I am not going to. It's not 2. It's one of them. Yes.
We don't need to do this.
Yes, you do. I am just not spending the time right now to do it. Sometimes the algebra is going to be terrible. Right here. Theta plus what? What was it? Theta minus theta cubed over 3 factorial plus what? Theta to the 5th over 5 factorial, right? We're multiplying it times this, so it's theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. Everybody sees that? Yeah. So let's do this out. You get what? Theta squared, right? What's the next power you get? Theta to the what? Over. There's 2 of them, right? Correct? Because there's going to be that one times this one, right? Are there any powers between? Is there going to be a cube in there anywhere? No, there's not. So if you only need the first 4 non-zero terms, do you have to go any further? No, because there's going to be the constant, the theta squared, and the theta. Oh, it's already in the other one. My point is there more algebra? Yes, but it all depends on what the question is asking. This question is asking for the first 4 non-zero terms. So what's the first one going to be? 1. What's the second one going to be? 1/2 theta. Do you agree? Yeah. It's plus. That's the next one. What's the next term going to be? 1/8 theta squared, right? And then you just need to, oh, what's the next one? 2 times theta to the 4th over. Oh, is there a theta? Oh, the theta cubed is already there. So are we done? Done. No? Are there theta cubes anywhere else? Yeah. Where is it? Tell me where it is. Yeah, see do you see the ... right here, everybody? What's that one? It's 1/8, but what's that? It's 1/16, right? Theta, right? And that whole thing is to the what power? Cube. So you have to make sure you collect all of them. So this one is going to be plus something. I, again, am not doing the algebra out. You just have to be careful about it. The only thing I'm asking is this right now. Do you understand the algebra you need to do on this one? Yes? Do you understand the algebra you need to do? Any?
So can we slide right?
One of my more favorite ones from this section. That looks terrible, right? Or not. Let's see. What is the index variable on that one?
K.
Nope. Is it n or k? It's n. Why is it n and not k?
N is on the summation.
Yeah, n is on the summation, k is not. So in this case, k is a what? It's anything you pick it to be, okay? So what could I factor out in front of this summation right here? Yeah, I could do e to the negative k. And can someone other than Stephen explain to me why I can factor that out? Why is that allowed? Chip.
It's because it's case if we make it constant.
Yep. It's never changing, right?
Yes.
Are you allowed to factor out constants? Yeah. Yes. So let's say I gave you this right here. Let's say I gave you that right there. And I said, oh my gosh, what does that equal? And you were totally stuck. What can you always do with summations if you're totally stuck? What could you start doing? What did you say, Soma? So let's write out the terms. This is e to the negative k times what? Plug in 1. What do you get? You get what? 1 over 0 factorial, which is a fancy way to say what? 1. Plug in 2. What do you get? K over what? 1 factorial plus, what's the next term going to be? Over 2 factorial. What's the next term? Okay. Someone, raise your hand, don't speak out loud, I'll call on you. What does this look like to you right here? Can someone tell me what this looks like to you? What is that? Wiley. Yeah, specifically it's e to the what? This is e to the k. What are you multiplying it by on the outside already? So that's e to the 0, which is 1. Oh, snap! So what does this mean? No matter what the k value is, what does this always collapse to? 1. No matter what the k value is, this infinite summation always collapses to 1. Yes, Chip?
What do you add when you multiply?
Exponents? Same base. So a to the x times a to the z, whatever you want to call it. What do you do with the exponents? A to the x plus z. You add them. Same base. So we had e. So what did we have there? We had e to the negative k and e to the k. So what is that? E to the negative k plus k, which is e to the 0, which is 1. I just wanted to specifically call this one out because that's really cool. I find that really cool. It's also important because if you don't memorize your Taylor series, what happens? Sad. You get very sad. Because this should take about 5 seconds, and it might take a lot longer if you don't memorize it. Okay, everybody get up and stretch. And while you're stretching, tell me if you've seen this before. Have you seen this before?
Yes.
Stretch. How many people have been in this class since the beginning of class? Raise your hand. Keep your hand up. Therefore, how many of you should have seen this before? The people with your hands up. There you go. Okay, so why is that super helpful? Solidarity in silence. If no one speaks, we never have to answer the question. Come on. Why is that really important? It tells you a bound. So when you're adding up an infinite series, are you ever actually to the limit of that series? No, you need to keep on going forever, right? So for example, is the alternating harmonic series convergent?
No. Yes. Yeah.
Yes, it is. 1 minus a half, plus a third, minus a fourth, plus a fifth. Does that converge?
Yeah.
Yes. Side note, do we have any idea yet what that converges to? No. The elements do, but the sum. Do we have any idea what this series converges to? No. But we know it converges because it's an alternating series and the terms get smaller. We good with that so far? So one estimate for the sum is I can add all those up, right? That would be S4. Do you agree? This thing eventually adds up to some constant C. The question I have is, okay, so if you do this, that represents how far away from C, that represents the error bound, right? What does this tell us has to be less than? What does it have to be less than? The what? Someone said it? This error has to be less than what? It's on the board already. What? 1/5. It's always less than the next term. It's always less than the next term. This is super awesome, and why I put the smiley face there is all this means is if you're adding up the first 10 terms of an alternating series, what's the maximum error equal to? The 11th term. If I add up the first n terms, it's always less than the n plus 1th term. That's it. But why is this only apply? What's the key word on the first line? Alternating. If it's not alternating, does this apply?
No.
No, it doesn't. No, it doesn't. Sit down, everybody. I need to run and get the charger. Anybody have their charger on them, actually? Can I steal it for a sec? With that, what does this mean right here?
The sixth derivative.
Well, in this case, on the board, it would be the what? The n plus 1th what? Derivative of the function what? F. So when you find m, what you're going to be doing is you're going to be looking at a function which just happens to be like maybe a 6th derivative or a 7th derivative. If we're going to be taking really high derivatives, we really hope the function is what type of function? Polynomial or like a really nice trig function, right? Otherwise, what happens? What happens when you try to do the Taylor polynomial of e to the t cosine t?
It got really
boom! And you're like, no! Okay, so this search, this entire thing comes down to this right here. You're going to be taking a derivative and saying, okay, here's a function. What's the biggest it can be on this certain range? You don't have to understand what's going on yet. We're going to try an example and fill in the pieces. It's okay for this not to make total sense. It's fine. This takes a while to understand. So what we could ask is this question right here. Let's say I asked you this right here. And it's, gotta turn it on. There we go. Boom. So we could say this right here. Let's take a look at this. Give a bound on the error E4 when e to the x is approximated by its 4th degree Taylor polynomial about 0. Do we like 0? We do. On that interval. You see the interval right there? There's the interval. Does this look familiar right here? Yeah, that should just be automatic. No thought. That should be muscle memory at this point. Well, or soon. We okay with this? So if I plug in 2 into this, this is going to give me an estimate for e squared. If I plug in 3, it's going to give me an estimate for e cubed, right? But they are just what? Estimates. This doesn't go on forever, so is it exact? No, it's an estimate. So we're interested in knowing something about E4, which is how far away could we be from the actual value of E4? The key here, everybody, is we don't want to use e to a power to calculate the error. Because if we could calculate e to a power, what could we just plug in? We could e to that power, right? So the whole point of this exercise is to find an error bound without using e to a power. You understand the quest here? So in this case, 4th degree Taylor polynomial. So for this formula right here, what does n equal? 4. N equals 4. Okay. So let's do some plug-in math here. N is equal to 4. What does a equal, just so we can have it written down?
0.
Are we okay so far?
Yeah. Why is a equal?
Because it's centered around?
Oh, 0.
0. Okay, so let's take a look at this. So we're looking for E4. Everybody sees the 4 right there? This is just a statement of truth here. You're not doing anything with this segment, but we need this. What does n equal? 4. So it's 4 plus 1 is? 5. We plug in what for a? 0, and then it's 5 up there. So we have this thing right here. The thing we are looking for is here. But what have we not found? M. Remember, M is a what type of value? It's a least upper bound. You have to find the smallest thing possible that is greater than something. And what is that something? It's the maximum of the 5th derivative. Why the 5th derivative? Why the 5th derivative? Because it's what? N plus 1. What was the original function we were working with? What was so nice about the function? It's f of x is equal to e to the x. What's the first derivative? E to the x. So what's the 5th derivative? E to the x. So I'm asking you this question. This is e to the x. Do you agree? What's the interval? Do you remember if I scrolled up? Do you remember what?
It's negative 5.
From negative 0.5 to 0.5. Negative 0.5 to 0.5. What does the graph of e to the x look like, everybody? What does it look like? Looks like that, right? You agree it looks like this? Is it always increasing or always decreasing? Because the derivative is always positive, right? So I ask you the question, m is, on this interval from negative a half to a half, m is, what's the maximum this function can be on that interval? What's the maximum it can be on that interval? E to the half, specifically because the function is strictly increasing. What happens if this thing goes berserk on the inside? You have to find derivatives of the derivative and find critical points. Is it really nice when it just strictly increases? So in this case, our n value is e to the 1/2, because that's the least upper bound. But, what did I tell you? We want to find an n value that doesn't involve what? E to a power. Yeah. We want to find an n value that doesn't involve e to a power, because if we can do e to a power, we can just do e squared, right? So my question to you is, this is where you get to do really big kid math. E squared, so we know this now. This is what we know. We know that the 5th derivative on that interval has to be less than or equal to e to the 1/2, right? what was the interval? 0.5 and negative 0.5, right? Can someone tell me what integer is that, besides Stephen, because I'm sure you know, what integer is that definitely less than? What's the smallest integer that it's definitely less than? Well, e is 2.7, so the square root of e is going to be bigger than 1. So it's got to be less than what?
2.
It's definitely less than 2, right? Definitely less than 2. So what does this tell us? We go back here, and where do we plug that 2 in? Sorry, I lost the... Where do we plug that 2 in? For m, exactly. So we plug 2 in right there. Everybody sees that m value? So this is what it tells us. The error when you have the 4th degree polynomial, the 4th degree Taylor polynomial, the maximum error is 2 over 5 factorial times x to the 5th. So this is what it means. What's the point of Taylor polynomials? What's one point? You can estimate things, right? You can estimate sign without using sign. You can estimate e to a power without using e to a power. So do we have an expansion for e? Yeah, we have this, right? So theoretically, if I asked you what e squared was, could you plug in 2 into this? Is that an estimate? Yes. If I asked you, I don't know, e to the 1/4, could you plug 1/4 into this? That would give you an estimate of e to the 1/4 without using e to a power. Are you with me so far? I've done some of the decimals already, so you don't have to. So if you look at this, for example, e to the, where is it? E to the 1/4 is right there. You see that red in the middle? If you plug this in, you get 1 point. Does this end, by the way? It keeps going. E is irrational. It keeps going. So this is the actual value right there, just for reference. If you your estimate is when you take 1/4 and plug it into the Taylor polynomial above. Are you comfortable doing that? Can you plug in 1/4 into the Taylor polynomial? What's the easiest mistake people make when they plug 1/4 into a Taylor polynomial like that? They might get a radical wrong, or they put a minus sign in the wrong place. This is the estimate right here. If you plug 1/4 into e to the x to the 4th power expansion, this is what you get. So you see this decimal? This is the actual decimal, and this is the what? Approximation. So what is this? I subtracted these two numbers, so this is the what? That's the actual error. This is the what? Actual error. And what's this? This is our estimate, right? And this is the actual number. What did we go through the trouble of finding right here? That was the maximum error right here. Everybody, see that maximum error? What is that maximum error equal to? Well, that's equal to this. When I did it out, it's 0.0006. The maximum error should be greater than which one? The actual error. Is 0.0006 greater than this? Yeah. Yes. So logically, what it's saying is, you see this? This is our guess. If we didn't have the ability to e to the x on our calculator, could you have an estimate for what the actual value is? What would the maximum be? This plus what? That. Or, what's the lower bound? This minus that. So this is the maximum error at that specific point for 1/4, so e to the 1/4, just for the Taylor polynomial degree 4. Nam first, and then Stephen. Yes?
I'm still kind of confused.
That's fine.
Does n has to be like an integral, or like an integer, or like can it be like a decimal or something?
N?
Like m.
M?
M, yeah.
M. So here's the thing. That's a really, really good question for you to ask. The whole point is this. If we're estimating e to a power, it doesn't have to be an integer. The only thing I really want you to avoid is if we're estimating e to a power, I want m not to use e to a power. Because the whole point of this exercise is to try, if we can, to not use e to define e. Like, what's the point of Taylor polynomials? To totally do something different and come back to e. That's the whole point for me. It's the big point. Sometimes it's unavoidable, though. For example, e to the 1/2 is really nice. It's nice logic because e is between 2 and 4, or between 1 and 4. So therefore, e to the 1/2 has to be less than 2. Because what's 2 squared? 4. So like, there's a great logic there, right? But it's not always that easy. It's not always that easy. But you're looking for what? a least upper bound. You'll get practice with this. So all I'm getting at here is what's the only letter you really have to remember here? M. Everybody sees the purple right there on the board? I'm going to give you 30 seconds. Memorize it. About 2. So on number 2, we're gonna find the error for a certain degree Taylor polynomial. What's the degree? What's the degree? Third degree. So that tells us what about which value in the formula? What does that tell us? N equals 3. So literally write that. N equals 3. And what's A going to be? 0. So we're looking for E3 of x, and we know that that's going to be less than or equal to f of x minus P3 of x, and we know that's going to be less than or equal to m over, what goes on the denominator? Equals, sorry, thank you, equals, thank you, sorry, equals, m over what? So in this case, n plus 1, n is 3, so it's going to be 3 plus 1 factorial, right? X minus what? To the fourth. I'll write it as 3 plus 1 for now. Do you understand the numbers we've plugged in so far? We've plugged in those numbers so far. And so far, we can simplify it a little bit. We end up with n over what? Yeah, well, 2 factorial? 4 factorial is what? 24. X to the what? Fourth. Are you with me so far? You now have to find a value for m. M is a least upper bound, and m is going to be f4 less than or equal to m, like this. The question, though, is what's the interval? What is the interval going to be? So I said this has to be true. We're trying to find a least upper bound, an m value that caps this on a certain interval. What do you think the interval is? Someone who hasn't spoken yet for this one right here. We're around 0, and we're estimating sine of 0.2. What do you think the interval should be? Raise your hand when you think you have it. What do you think the interval should be? What do you think the interval should be? We're using 0.2, so where does that have to be? In the interval. So what do you think the interval should be? What was the interval in the question we did before? Negative a half to a half, right? What could we use for an interval on this one? Yeah. Oh, that's a really good idea. Negative 1/4 to positive 1/4. Why did you choose that? It's very close, and it might be really nice to use, right? It might be really nice to use, okay? So let's just try that and see if that helps us. Remember before any, when we used e to the x, I said m could be anything other than something that uses what? E to the x, right? So in this case, what are we estimating? Sine of 0.2. So we really want to see if we can eventually not use sine, right? If possible, we don't want to use sine. Is everybody with me in that? It's kind of like the whole point. Sometimes we're going to be forced to, and it seems kind of tautological, like why are we doing it? You'll see. So in this case, what's the function? Oh, it's sine, right? What's the derivative of sine? Hey, you got cosine of x. What's the next derivative? Negative sine of x. I love how that divergence happens. The third derivative? Negative cosine. And what's the fourth derivative? Sine of x. What does sine of x look like? Around 0? It's a what? What do you call it? At 0. What's sine of 0? 0. And then it goes up or down? It goes up, right? So here's sine. Do you agree? Like this? What was that interval you picked, Ian? Negative 1/4 to 1/4? So that's something like here to here. Sure, right? Does sine go just up or just down or both in that interval? It's going what? It's going strictly increasing, right? So where is that maximum going to occur? Yeah, 1/4 comma what? Sine of 1/4. Have we run into a slight problem? So theoretically we could continue. What could our m value be if we wanted it to be? Sine of 1/4. What's the problem with that? What did I tell you? We don't if possible, we don't want to use sine for m because that's what we're trying to estimate, right? Sometimes it's unavoidable, okay? But we're just going to go with it. If we were to continue this, we need to type sine of 1/4 into our calculator to get a decimal. So the question is, are there any values here that we could use that are better that you could find nice values for? Yeah, so instead of a quarter, anybody want to guess what we could use? Yeah, Alex. Oh, pi over 4. What is pi over 4 about? Pi over 4 is like what? So wait, you did sine of pi over 4, right? Is what you're just talking about? Like, what is sine of pi over 4? Root 2 over 2, right? Pi over 4 in decimal form is like what? 3.76 something, right? That's pretty good. It's pretty good. It's 3/4. That's a little bit more than 3/4 is all we're doing there, right? Is there something even better we could use?
Yeah,
Pi over 6.
What about pi over 6, right? Could we use pi over 6?
No, sure.
What about pi over 3? Pi over 3? No, that's bigger, right? Pi over 6. How many degrees in pi over 6? Oh, come on, help me out here. I need some help with my trick.
A little over that.
Pi over 6 is how many degrees?
Oh,
30.
30, right? So what's sine of 30 degrees? What's sine of pi over 6? What is it? 1/2. So is that kind of cool? Because pi over 6 is closer. What's pi over 6? That's closer to 0.2, right? It's like over 0.5 a little bit. So instead of doing negative 1/4 to 1/4, what could we do instead? Negative what? 6 to what? I like this better because then when we go to here, what would it be? Pi over 6, comma, sine of pi over 6? But what is sine of pi over 6? 1/2. So what do we do?
Use a sine value that we have to plug in those out.
Exactly. So we use one here that we know the actual number for, is what I'm saying. It does, overall, it's not the end of the world if you're forced to use sine for your m value. But is it pretty cool if you don't? Yes, because you can use it. You can do stuff by hand still. So if we chose pi over 6, let's finish this first. We're going to say m is equal to what? What's m equal now? 1/2. So we take that. We say m is equal to 1/2. So what does this equal? 1/2 over 24 x to the what? 4th. So what is that? 1 over what? 48 x to the 4th. This is the maximum error depending on what you plug in for x. Oh, what are we plugging in for x? So could we make an estimate right now? This would be the max error of the estimate. The max error of the estimate. So when x equals 1/5, what do you end up with? 1 over 48 times what? 5 to the what? 4th. I'm just plugging it in. The point is, did we have to use our calculator at any point on this? No. This is the maximum error right now of the third degree Taylor polynomial, the third degree Taylor polynomial for sine when you plug in 0.2. Let's see what the actual numbers are. Let's see what the actual numbers are. So Wiley, on your calculator, do this for me. What is sine of 0.2? Can you do that for me, Wiley? What is sine of 0.2? Tell me what it is. 0. What? 19866. It goes on like that, right? Nice. So if this is our estimate, and this is the actual, we could find the actual error, right? What's the actual error going to be on this one? Someone do that for me. Find me the actual error. What is the actual error going to be? Oh yeah, 2.6, yep.
6, 4,
Times 10 to the negative 6, I think, right? That's the actual error. Does everybody agree with me right there? So we went up here. Someone do this for me on your calculator. Can someone do 1 over 48 times 5 to the 4th? What do you get? Yes, I understand the fraction. Someone do it on your calculator. Do it for me. What do you get? 3 point what? Yeah, times what? 10 to the what? Oh, 10 to the negative 5. Which one's bigger? This is our max error. This right here is our max error. And what did we calculate the actual error to be? Oh, look, which one's bigger? This is bigger. I'm just trying to show you, to verify reality here, we picked something that has got our good max error. This was nice because we have to use our calculator. Well, to get the decimal, yes. Hold on. Maximum error should be always greater than the actual error. Yes, Gary. How do I get the estimate? Sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. We were just dealing with the third power. Because look, the question said this, third degree right here. See that? Third. So what degree did we stop at right there? Third. We stopped at 3. We stop at 3. Okay, this is super heavy.